Okay, so first of all, thank you for letting me, for giving me this opportunity to talk about the work we have been doing on optical properties of transition metal dichalcogenides. So, can I? Yes. So our interest on these materials comes twofold. On one hand, they have been in the past gaining track as significant candidates for a lot of applications, ranging from optoelectronics to spintronics and processing of quantum information. However, it's extremely hard to synthesize any sample without any defects. And even if you manage to obtain a sample that will be perfectly flat, you are bound to find, wait, let me see if I can turn on the laser pointer. Yes, you will be bound to find substitutions and replacements in substitution and vacancies in the material just synthesized. And now you can see these defects as either something that you don't want, and so a hindrance, or you can actually see them as something that's going to enrich the optical properties of your material. And several defects have been proposed as candidates for single photon emitters or quantum dots. Now, why are transition metal dichalcogenides so interesting, and why have they been gaining track as candidates for all these applications? Well, it's related to their chemical composition and geometry. So they have an hexagonal structure, they have an hexagonal lattice, but unlike graphene, they have a gap due to the lack of inversion symmetry. And this gap changes from indirect when they are in the bulk and goes to direct gap. So they will have high luminescence when they are in the monolayer case. But thanks to the chemical composition, you have strong spin orbit coupling. So you have a splitting of the bands near K that is of the order of the hundreds of milli-electron volt. I think the lowest that you can have is about 200 MeV, and it's about 400 or 500 in tungsten based. Now, spin orbit coupling not only lifts the splitting of the bands, it also introduces something else. So if you were to look at the spin polarization of the bands near K, you'd find that they will reverse. So K and K prime are the 2 points at the vertex of the Brillouin zone. And while the band energies are exactly the same, the spin polarizations are not. And this will depend, the type of spin polarization will depend on whether you have a W-based or an MO-based. In one case, they are intercalated, and the other, they are somewhat sandwiched. And now this led to the idea that you could select with circularly polarized light the valley at which you were going to create excited electrons and holes. So you have populations of excited carriers with a well-defined spin. And so the quest began to have these populations with well-defined spin to survive for long lifetimes at high temperature, a little bit like the superconductivity at high temperature. But it's some research that's been going on for a while, and it's been eluding us, the ability to create these populations that survive for very long and that have a very well-defined spin. So we needed to understand how we would be able to manipulate the material so that we could give this long-lived lifetimes, but now at high temperature instead of just low temperature, and how we can manipulate the spin relaxation mechanisms. Now, a way to measure this experimentally is via the Kerr rotation measurement. So this is the simplistic view of a theoretician of how the Kerr measurement goes. You have your material that will have given spin texture in K and K prime. And so what you do is that with a pump, you create a population of excited electrons and holes at a given valley. And then later at a given delay, you probe it with a linearly polarized light. Then you measure the angle between the polarization of the probe and that of the reflected light. And this will give you a measurement of how imbalanced the populations are at K prime and K. And we were collaborating with our colleagues in Aachen at the RWTH. And they had this sample that exhibit two slightly abnormal behaviors. So first of all, in the short time scale, the Kerr rotation angle would flip sign more or less at 600 Kelvin abruptly. And also at the long time scale, they found that the spin lifetimes were also having a non-monotonous behavior. So they would start at around 8 nanoseconds, then decrease with temperature, and go to around 1 nanosecond. But if you were to increase the temperature, they would increase again and reach the hundreds of nanoseconds. And so we had these two uncharacteristic behaviors that we needed to explain. And so we set on to see if we could understand this just with the intrinsic mechanisms that exist in the material, which in this case was molybdenum diselenide. Now, the way we do this, the way we did this is by using the RT real-time propagation that is coded and built in the Yambo code. So there's a lot of work that's been going on to have this. And basically the process is divided into two parts. First, you have the excitation, where the electron hole is created and they are interacting at first order. So you are able to pump exactly at the energy of the exciton. And then there's relaxation. And for this, we have a real-time equation for the density that includes all the scattering processes that will be in this integral. So you have electron hole, electron phonon, and even if you want electron phonon interaction. And with this real-time equation, you can get the snapshots of the configuration of the system at specific instance. With this, you can get the occupations and you can extract information about the magnetization, the Kerr angle, the polarizability, or photoluminescence at specific temperatures and specific instance. So what did we observe when we did our simulations? So this, as I mentioned before, was for molybdenum diselenide with a laser pulse and a phonon bath at given temperatures that would match what they were doing experimentally. And we were looking at the magnetization. So here you have the magnetization at different temperatures, and compared with, and in the background you have the laser pulse. And so when we looked at the magnetization values of the sample at 8 picoseconds, we managed to track it, and we found out that the temperature that we were observing the same sign reversal that it was being observed for the Kerr rotation measurement at 60K in the sample they had. And so, okay, this was interesting that the short-term behavior was being reproduced, but we needed to understand the mechanism that was behind this. So what is this mechanism? Well, there is a change in the transition processes that electrons and holes can have at low and high temperatures. So the first thing we need to know or need to remember is that a transition from K to K prime is basically forbidden because the wave functions at the edges are basically pure spinors. And so via electron phonon, you cannot have this process. You cannot go from an electron that is spin up to an electron that is almost spin down. But the states near K and near K prime are not. So what we observe is that the first thing that happens is that the electrons in the hole scatter around the place where, around the states where they are created, and then they can move towards the other valley. Now at low temperatures, this is the only mechanisms that they have access to. So the electrons can scatter a little bit up thanks to acoustic phonons, and then they need a large wave number phonon to move to the other valley, and the holes have a similar mechanism. However, at high temperatures, the electrons have now access to the states in this Q valley that lies more or less midway between gamma and K. And it turns out that this valley is much faster. The scattering rates with this valley are much faster. And so the electrons can, beg your pardon, they can reach the other valley quicker than the holes. So while at low temperatures, the holes were having a much faster scattering process. And so the electrons were staying behind in the valley they were created. So the magnetization and the Kerr angle will have a given sign. At high temperatures, this would flip. The electrons can reach the other valley much faster, and so the holes stay behind. And the sign reverses for both magnetization and the Kerr. Now, we were able to see this by creating a fictitious system just to see the effects of the electron phonon interaction by promoting artificially an electron from the top valence to the bottom of the conduction. And so here on the right, I track the populations at around the vicinity in K prime of the electrons in the holes, and the colors match. So blue is the last valence state, red is the first conduction, and gold or yellow is the second conduction band. And we can see how dramatic this transition is. So at 60 Kelvin, the populations of the holes are trying to balance much faster than the electrons. So here the full red line is not yet in balance with the dashed line, which are the populations in the other valley. But at 100 Kelvin, while the system is able to reach a balance between the two valleys, the electrons now can achieve this balance much faster than the holes. And not only that, the fact that there's now not even one electron in the vicinity of K prime means that they are spreading through the whole of the brilliant zone. And we were quite happy with this, but there was an issue, that is that the electron-phonon interaction was only able to explain the spin relaxation mechanisms at short time scale. So all of this is happening in the picosecond scale, and the measurements were in the nanosecond scale. So we needed some extrinsic mechanism to arrive at this very long lifetimes. And one of the questions that we had was, is this magnetization, are these spin populations being transferred to some defect state that is able to trap the excitons, the electrons and the holes for very long and be able to protect them against phonon scattering? And are we able to get it out? But also, are we able to just see from the optical properties what kind of defects that we have? So if we can assign a specific optical signal to a specific type of defect, so that once you have your device built, you could just measure them. You can just measure the absorption spectra. And from it, you know, okay, now I have an S vacancy, or I have a metal vacancy, or some sort of substitution going on here. And so while it's somewhat impossible to run through all the possible defects that you can have, we had to set up and choose a couple of them. In this case, we went with 4 defects that we considered to be the prototypical ones. So you would have 2 vacancies, one in WS2, one sulfur vacancy, or one tungsten vacancy, a molybdenum tungsten substitution that it's found in nature, but you can also create in the lab, and a CH2S substitution, so a methyl group replacing a sulfur ion that is possible to engineer with plasma treatment. We stayed with neutral vacancies, since it was reported in previous work that with neutral defects, because it was reported that charging the defect should just shift rigidly the defect states, if there are any, in the mid-gap region. And so the energies of the optical signatures would shift, but they would remain essentially, the number of features would have to remain the same. Now, this is done by taking the DFT electron bands from Quantum Espresso and then correct them with GW and computing the electron hole interaction with the beta salpeter equation with Yambo. Why do we need to go this far? This is for the new people, the people new to the community in the audience. So DFT is a ground state theory, so there are no excitations in it, and which means that you are not going to be able to capture optical properties. And it also doesn't account the presence of their quasi-electrons in their system. So it's an electron sees just only himself. It doesn't really see that there are other electrons in this system. We can do the first step, which is to correct the band energies by taking account of the screening. And this leads you to the correct energies for the bands, but you still have no electron hole interaction between the electron that's moved upwards and the hole that stays behind. In order to have all of this and to have access to the optical gap, we need BSC done on top of GW. So we have the screening introduced by the presence of the hole and the electron hole interaction. And this can give you access to all the states that lie between the band gap. Now, for 2D systems, the proper description of the W is paramount, because you're going to have a positive and a negative charge that form a dipole, and the majority of the dipole field lines are going to cross the vacuum. They don't cross the material. So if we don't have a proper description of W, you might have unbound excitons, or you might have a renormalization energy that is too high. So once all of this is done, we can analyze the optical spectra, and here it is, the consequences of what happens when we change the system by introducing the vacancies or the substitutions. So I begin with vacancies. Here, the first thing that I want to show is a schematic of what happens at the level of the band structure. So in both cases, for the S vacancy and the W vacancy, new states arise in the gap region. For the S vacancy, you have two manifolds of doubly degenerate states, one that is highly polarized in spin and one that is not that polarized. And for the W vacancy, since you are going to leave much more dangling bonds, you are going to see the rise of what it's tantamount to 10 new states. However, these new ones are very shallow, and they are actually occupied defect states. So the Fermi energy is actually around here. And this means that at the level of BSE, we might actually be able to see defect to defect transition. And do we see it? Well, this is the optical spectra that we get for both vacancies. And there are two things that I need to remark. First is that we recovered A and B excitons almost at the same energy, but new features appear thanks to the vacancies that are different, that distinguish the defected system from the pristine one, since these optical signatures don't exist, but they also distinguish the two vacancies from themselves. So in the case of the S vacancy, you get two new states thanks to this transition. Here, the D2 state is much lower in intensity thanks to the fact that this state is much less polarized in spin, so the transition matrix element is much lower. But for the W vacancy, thanks to this whole new range of defect states, you have now a much larger set of peaks. And so you are going to have what would be the usual pristine state to defect state transitions, but now you have also this D4 and D5 states that are defect to defect. And so the overlap between the electron and the hole is immense, and the bands are massive, so they end up having very high excitonic intensity. And when we look at the wave functions of the excitons, so we localize the hole near the defect site, we can see that yes, these are extremely confined states. So especially in the case of the D4 and D5, since the hole will also be confined to this region, they are creating quantum dots and they are strongly bound. So we identify them as potential candidates for qubits. Now, for the substitutions, the results were surprising, but in a different way. So the first thing that we noticed was that there were no mid-gap states. For the molybdenum tungsten substitution, this can be reasoned afterwards because it's an isovalent substitution, and the chemical bond radii for both W and MO is relatively the same. So the change in the potential is not going to be that drastic. But for the CH2 substitution, this was a bit striking. At the level of, as a consequence at the optical level, is that the A and B excitons are basically recovered with very little changes in their energies. However, at the level of the wave function, something changes. So in both cases, the exciton wave function does spread through the whole solid, so it's not a typical thing of a defect. But also there is some charge concentration near the defect site, and especially it's even more striking in the CH2 case because there is an actual breaking of symmetry due to the presence of the methyl group. So while we don't expect these two kinds of defects to have a clear, distinct optical signature, they might be, it might be possible to see them with something akin to real-time STM, or even by looking at the lifetimes of these excitons, since the wave functions will now be different. So some symmetries will be reduced, meaning that the transition elements that you're able to compute and that will give you the lifetimes are going to be different as well. Now, what would be next? This is just a perspective what is coming based on present work. So it's not a TMD, but still a 2D system. This is a negatively charged boron vacancy that we are working with in collaboration with Francesco Livi and Nicola Marzari at the EPFL. And we are trying to reproduce the observed PL intensity that had a peak at around 1.5 electron volt, which exists nowhere near in this region when you look at the absorption of this system. And so this is going to be soon published on arXiv. And so we had to figure out why this difference was going on and what mechanism could drive this, the rise of this new peak. So we had a set of hypotheses. So would it be thanks to the non-equilibrium configurations, since with PL you create excited electrons and holes, this is going to change the screening, it's going to change the the energy of the bands? No. Was this a Young-Teller distortion due to the fact that you have now excited carriers, you are able to break the symmetries of the structure? No. And at last we arrived at the dipole momentum enhancement due to electron phonon. And this was the case. So once we take into account almost all phonon contributions, we find that some of them do enhance the transition, and we do get a peak near 1.5. And when we aligned the zero phonon line energies of both the experimental measurement and our calculations, we see that they match quite well. And it can be proposed, if we track the full width half maximum of the lens and dispersion, we can actually propose the system as a good thermometer as a potential application. So science and research is actually a many-body problem in and of itself. We have a series of scientists, so the particles that are able to interact things to all of these different bosons that grant us computing time, the codes that we use, and the funding. And I leave you here with the summary. So especially about the defects, which is our most recent work. The vacancies that we studied have distinct optical signature, both from the pristine and amongst themselves. And we have proved that they have bound states, bound excitons that have an energy splitting amongst themselves that it's around 200 milli-electron volts, which is much higher than room temperature. So in principle, they should be protected against electron phonon scattering. For the substitutional effects, while there are no mid-gap states, this also has a positive consequence, is that the full optical gap isn't perturbed by functionalization. And so if any molecules or any molecules are able to graft themselves to the defect site, you have the whole optical gap as a bandwidth for detection. And here I finish my talk, and I look forward to your questions.
Thank you very much, Pedro, for this nice talk. So if you have a question, so please raise your hands virtually in the reaction section.
There's Mirta, I think.
Okay, I'm trying to, okay, yes, you're right. You see it before. Okay, Mirta, please go ahead.
Yeah, just a question on the defects. So are those stable, and are the, just say, most common somehow thermodynamically, or
so
you say prototypical, but I just wanted to.
So let me get let me get the list of them. Or where are they? Sorry, too far. So these three So the S vacancy, the CH2 substitution, and the molybdenum W substitution are thermodynamically stable. In fact, the CH2 substitution, the formation energy is negative. The W vacancy is the hardest to make. It has a formation energy of around 10 electron volt, which is.
And that's the interesting one for quantum
That's the interesting one, yes. However, this is for a neutral system. We might be able to reduce it if we start charging it.
Okay, thank you.
So there was also a question by Nicholas Pike. Nicholas, you want to ask it yourself? You can unmute yourself. Otherwise I can read. No microphone. Okay. So the question is, hello, Pedro, what concentration did you use for the vacancies?
Hi, Nick. So this is one vacancy on a 5x5 supercell. I don't remember. I can't give you the number exactly. So it's one vacancy in a 5x5 supercell. The 3x3, it's too low, especially for the W vacancy. The defects will start interacting, and the 5x5 is the minimum that you can have to have an isolated vacancy.
Okay, thank you, he says. Okay, good. There's another question by Lorenzo.
Lorenzo. Ciao, Lorenzo.
Ciao, Pedro. Yes, it's a question strictly related with your answer. The convergence of the size of the supercell is converged on optical properties on the DFT calculation, because I would say, but I mean, is it clear, my question?
Yes. So for these three systems, MOW, SCH2, and the S vacancy, the 5x5 is a good starting point for both DFT and optical. For the W vacancy, no. So some of these, let me move forward. And we do discuss this in the paper. Some of these peaks in the defect, in the W defect, are spurious. So they result from interaction between two vacancies. Okay. I think, if I'm not mistaken, is the D1 and D3. Still, the D2, D4, D5, they are present. Okay. And they are highly local.
And that is the, let's say, the position of the D5 is there, because I see a small shoulder at 0.5 eV. Isn't that the D5? This one? Yeah. Because where you place the line D5, I don't see any shoulder. Maybe there is, but
I think it's well, it's over. If it's hard to see in a linear scale, but it's eaten by the D4. But on here, the defect, the BSC eigenstates were spurious. I looked at them, and they were not. There are no significant contributions above 0.05.
How can you do this check? How do you do this check? You
can look at the contributions of each exciton state. So you build the spectrum, you have that, and you look at the A dot P. So the BSC matrix element times the dipolar moment. We can track them, how strong they are, and if they are significant or if they are just residual from the fact that it's not an infinite system.
Okay, I see. Thank you.
So if you would use less broadening, you would see it better. The
you would see it better, yes. But it might also, as with everything, you can have spurious values when you invert a matrix. There's Daniele now.
Hi, Pedro.
Yeah, don't take my job. Yeah, great. Go ahead, Daniele.
Thank you very much, Pedro, for the nice talk. I have two curiosity. The first one, according to your graph here in the left, you don't find defect states in conduction band?
In this, in the immediate here, no. But we looked at the DOS, and I think there were some, but they were higher. So you
higher in energy. Okay.
Higher in energy.
Okay. And the second one is looking at the high part, energy part of the spectrum. Let's say it's very similar to the pristine spectrum with the AB peaks. If you compare with exactly with the pristine, you have some shift in energy, or it is, I mean, you have some electrostatic effect that also shift this part of the spectrum. You have the AB position
So
as in the pristine one.
We see the A and B position, and in the BSC kernel, we only went up to as many bands as we could to converge the A and B. So anything that is above B,
no, but the A and B are in the same energy position of the pristine material.
Yeah, almost in the same energy position. There is in some cases there's a tiny shift. For instance, here in the S vacancy.
Okay, the overimposed spectrum is like I didn't. Sorry.
Yeah, so there's the pristine
one.
and yeah.
Okay, no, sorry.
There's a tiny shift.
Okay, thank you very much.
I have a question myself. So for the spectra, you explained what is the numerical procedure that you use with DFT, GW, Betz-Salpeter. I was wondering about could you say something about the Kerr angles that you calculated? How do you get them and what are the approximations involved?
So the Kerr angles, it's, okay, let's go here. So there are several approximations that we do first at the level of the real-time equation. So all of this is compressed in that you get a closed equation that's only dependent on the density. So we use it basically reduces this equation into a Markovian process. So there is no effects of memory. The energies are also replaced by GW-like energies, and we also have to use not only the Kadanoff time ansatz, but the Green's functions. Some of the Green's functions are approximated to their retarded parts, so you only have the poles. And then with this, we are able to obtain, as I said, a closed Markov equation. And with this, we compute the matrix elements. And if we look at the diagonal part, we are able to obtain the occupations at specific instance. And then we use these occupations we feed them at the level of the screening, at the level of the energy corrections, and we can compute the with the Betz-Salpeter equation, we can compute the Kerr angle, just with the different parts of the dielectric matrix. I hope I was clear. It's
yes, so
a lot of
it's
a lot of stuff going on here.
So you have to include spin orbit explicitly in
Yes.
the Betz-Salpeter calculation. Okay. Okay.